Hello, welcome back. All right. All right, good. I think that's good. All right. So this one is about the second portion of the next portion of this red blood cells. So we are going to talk about the degradation. So when the cells are aged, the average life of a red blood cell is 120 days. So you're gonna see this in the quiz question. Okay, what's normal age? Normal lifespan of a cell, of a red blood cell, which is 120 days. Yeah, so when it dies, what are we going to do about it? Basically, we are going to, just like our ecosystem, right? We were trying to reuse and recycle. So that's what we do. All right, so that's take a look. So here are just give you a visual idea. So here are the cells. We have a lot. And so when they are dead, when they are aged, when they lose this function, or when they are injured, they will get eaten by macrophages. So these are the cells function to eat injured cell, or eat cell debris, or eat bacteria, or eat yeah. So it's the function is to eat, right? We have three. We in the tissue we call them macrophage. Basically, most of them derive from the monocyte. We will talk about that later. Yeah. So those cells are in particular location throughout circulation. The primary organ to eat aged red blood cells are spleen. So here is showing you spleen, and this is an example of the macrophage. So they will engulf it. They will take it. When they take it, they will degrade it, destruct these cells. They will separate it apart. And here is an example of that cell, right? So here is cell. So you can imagine everything you can use, our body will recycle, reuse. Very common that the skin, the cell membrane, that's a membrane that everybody will use. So they will reuse it. The components of the cell membrane is phospholipid, so everybody will use it. Proteins, body will use it. Water, body will use it. Carbohydrates, body will use it, right? And so in the end, we have in particular we are going to talk about is that here we have a hemoglobin, right? So this is a normal hemoglobin. We have a lot inside of red blood cells. So our body will try to use them, but the thing is that hemoglobin is not pure protein. It has something attached to it. It has a heme. Heme is not a protein. Iron, iron we can use it. All right, so that's that. So this is aged RBC red blood cell destruction procedure. So first, they were circulating to the spleen, and then spleen has a macrophage waiting for them. So if they detect that this cell is aged or injured or doesn't function, they will engulf it. They will eat it, and the cell will eat it. And you know that in the cell organelle, let me show you here. Organelle, we have the lysosome. Lysosome contains a lot of digestive enzyme, so they will tear it apart. Yeah, and then for membrane will be used, water will be used, a lot of protein will be used. Let's look at the hemoglobin. So cells contains a lot of hemoglobin. So that's a major components in that red blood cells. That's function of the red blood cells to carry oxygen. So hemoglobin is that component to do it. All right. So so here, so hemoglobin has a protein. Let me see the picture. Let me show you here. So here is a hemoglobin. Let me show you here. Here is a hemoglobin. So it has protein components, but it also has heme. So protein will be degraded, and we can collect a lot of amino acids from it. So we can collect amino acids. So our body cells will use it. it will also have heme. Heme has iron, and iron will be reused. So iron will be transported back to the bone marrow, where we will produce new red blood cells, where we will use that to produce heme. And the heme to produce the hemoglobin. And the heme will be heme cannot be reused because that is a chemical. It's not part of our protein, or we cannot degrade it and it's used by some other cells. Our cell may be able to reuse heme, but we don't reuse the heme. So heme will be degraded. Heme will be converted to bilirubin. So you biliverdin first, and then very quickly got converted to bilirubin. And so then we will just release them into our stool or our urine, and then just poop it out or urinate it out. Yeah. So here is the picture showing that. So here is the old red blood cells. They go to spleen, and then the hemoglobin will be degraded. Iron will get recycled. Iron is very active in a way, so we need to kind of carry it through transportation. It's transported by the transferrin, and then convert it into the ferritin, that's a protein. So binds the iron, and then transport into the bone marrow. Yeah. Globin, that's a protein portion, will be degraded. Then we use that amino acid. Protein is a polymer of amino acid, so we will use that amino acid. Heme then will be converted into biliverdin in the spleen, but very quickly got converted into bilirubin, right? Bilirubin. Then this bilirubin will be transported to liver. However, while it gets transported, this bilirubin is also kind of active. So we need to kind of like someone need to chaperone it, need to carry it in order to prevent its interaction with some other things. So we need to chaperone it, we need to carry it, and we usually use albumin, the most abundant protein in the plasma, to carry it, to chaperone it, and then carry it into the liver. In the liver, these bilirubin will get conjugated. So here is a process of the conjugation. Don't need to worry about the chemical process. The basic idea is that here is the bilirubin is active in a way it can become toxic to our body. So we need chaperone to carry it, but the liver will conjugate with some sugar coating to it, coating to it, so it will make it not so potent in a way. And so that's what the liver do. Liver is very good, like a detoxification organ. So kind of like we can consider this is a metabolic waste products from the heme. So this is metabolic waste, just like our trash, right? It's metabolic. It's a waste. So we need to process it, and the liver is a very important organ for our detoxification. So we process it in a way to make it non-toxic, and so we conjugate it in the liver, and then the liver will use it and mix with the bile, and so go with the bile, and the bile enter into the small intestine and then large intestine and become part of the feces. When they are in the small intestine, part of that will be recycled because small intestine is the organ of the digestive system. So we absorb things back to our body. Part of those will be reabsorbed. And when they get reabsorbed, we will secrete them out through urinary system. But majority of them will stay in the small intestine and then go to the large intestine, and then poop it out. So that's that. So this is the heme degradation. So just summarize what we talk about here. So we have iron. Iron we will recycle it. We will transport it by transferring. Just by then you know it's ferring is an iron. Transferring is the one to transport it. So through that circulation from the spleen, you need to transport it into the bone marrow. So that transportation need to be, you know, managed. You cannot just let it freely diffuse away, right? So we need to kind of like chaperone it, like carrying it into the bone marrow. This is term you need to remember though, was a protein carry iron, this transfer, was a protein carry oxygen, hemoglobin, right? So those are the two examples that we mentioned today about molecule transportation through our circulation. Yeah, so that's that. The other one is heme degradation. So heme will be first in the spleen. It will very quickly, it will be converted into bili, uh, bili, biliverdin, sorry about that, biliverdin, and then very quickly converted into bilirubin. This bilirubin is unconjugated. So here is unconjugated. So it's a little bit interactive, can interact with some other. So this is metabolic waste. So this is trash. We don't want to contaminate our body. So we need to conjugate it. Before we conjugate it, we need to conjugate it then in liver. So spleen doesn't have that function. So you need to transport that to liver. However, in order to transport that liver, you need something to carry it. So we used albumin to carry it. So here is him converting biliverdin, very quickly converted into unconjugated bilirubin. And then bilirubin will be transported into the liver. Liver will conjugate it, and then it become safe, and then so go through our digestive system. That's fine. And then part of that got reabsorbed back to our body. That's fine because this is conjugated, and then we basically poop it out. Yeah, so that's that. So this one show you that, so basically that's it. You know, the RBC red blood cell degradation basically does it. So the bone marrow produce red blood cells, and by 100 days, it got uh, uh, engulfed by macrophage in the spleen, and then amino acid will be reused. Heme will have heme portion, and the iron get transported back to the liver by transferrin. Sorry, iron get transported back to bone marrow by transferrin, and then heme get converted into biliverdin, and then bilirubin, and then bilirubin will be unconjugated, get transport to liver. Get transport to liver, and then get transport to liver, and then it get conjugated, and then it will get secreted into bile, excreted into the bile, and then going to the bile, it will get poop out. Part of those will get reabsorbed because small intestine reabsorb, right? Not reabsorb, absorb our nutrients, and then part then get absorbed, then go to the kidney, get pee out. So that's the color of our urine, by the way, and also the color of our poop. Yeah. So that's that. All right. I think that's everything. A clinical condition would be that if there is a liver issue, you will see jaundice, right? Because that's the accumulation of too much of the bilirubin in the circulation. If they don't get processed, they don't get processed by liver. So they accumulate in the body. They will deposit uh, um, in our fat, because those are lipid soluble, and so they will get dissolved in our fat, and especially in the and we can see them. We can it can change our skin color to be yellowish, and so that is the jaundice. So you can see that it cause of jaundice could be hemolysis. So if you have too much of the red blood cell disrupted, this could be caused by the virus. It could be caused by the some other disease, or it could be the liver. Hepatocellular jaundice. It could be the liver. Liver doesn't process it, or it could be the bile obstruction. So if there is a bile ducts obstruction, if the bile ducts got obstructed, then you don't excrete those bilirubin into the small intestine, then they got stuck, they will basically stay in the body. So that's that. So those are common situations in adults. When you see that situation for the patient, basically, it's a sign, and then got to see doctor to find out what is the underlying cause of that jaundice. Another situation we may also see for the fetus, infant. Yes, infant. Yeah. Yes. So newborns, neonatal jaundice. So neonatal jaundice are the infant. When they are delivered, their liver is not, mature enough, so they don't process that bilirubin very well, and so you can see accumulation of bilirubin in the body. Or it could be that they try to replace their red blood cells. They need to produce more. They need to replace more. So they may accumulate that heme and bilirubin in the skin. So we have the jaundice. Most of them, this is very common though. I look it up. It turns out like 60% of the newborn has this. So it seems to be quite common. And the treatment is also safe. So we can use light. This light, basically, as we know that they can circulating, and part of those circulating in the skin, right? Circulation. And so we can use light to convert that chemical structure. So let me show you here. So this is whether that's unconjugated or conjugated, this chemical structure, we basically use light that will change that chemical structure to degrade them quicker. So that is the therapy. Yeah, all right. So that's that. Now, the next thing we are going to talk about is blood typing. Let me. All right. Okay, good. Yeah. So the next thing we are going to talk about is blood typing. So we now know everything about the blood, and the next thing we are going to talk about is there are 4 types of the red blood cells. There are type A, type B, type AB, and the type O. So what do we need to know here? We need to know how do we distinguish these 4. So what does it mean by type A, type B, type AB, and type O? The thing is that these cells has marker. So let me show you here. So rotation. All right, good. So I have pen. So these are the cells. So here is a cell. This is a red blood cells, right? And the red blood cell can have marker. We call this marker antigen. So here is a marker. Let's see that. So this is a marker of that cell. So we call this antigen. Gen is a generation gene. Yeah, antigen. So we have the antigen. Now we have 2 types of red blood cell antigen. we have antigen A. We can also have antigen B. So only two types, easy, right? Antigen B. So just like antigen B. Just one dot, okay? So that's the antigen. So here is the antigen B. Where do we get this antigen from? Antigen are protein, membrane protein. So these antigen are gene expression from DNA to RNA, then protein anchored on the membrane. So that's that. So here is the antigen B. So with that, you can expect that any one of us could have, we only have these two antigen in general, there are more, but in general, we only have these two antigen. So any one of that can only have one of these four situations. One is that you may have your red blood cell. Where's my pen? Man, where's my pen? Right here. You can have your red blood cell with antigen A. We call it A type. So type A person. Blood type A. You can have your antigen A. You can have your antigen B. We call it type B person. You can have your red blood cell with both. You're just lucky to have both gene. So you can have your antigen A as well as your antigen B. So you can, if you have both gene, if your parents are type A, B, or type A and type B, father type A, mother type B, you may carry one copy of A from your mother, one copy of B from your father, and then you will have type A, you will have antigen A and antigen B. We call this one type AB. So that's that. And you may be so lucky that you carry no antigen. So your father has one copy of A and one copy of nothing. So you may carry that nothing portion. Your mother may be type A, but she has one copy of A, but a copy of nothing. So you have that copy of nothing portion. You carry that copy of nothing. So you didn't carry any red blood cell antigen. All right. So you have no antigen. Your DNA just don't have those gene for coding those antigen. So we call this person type O. All right. So that's it. Blood typing done. All right. So that's how we distinguish the blood type. Either type A, who has the antigen A, type B, who has the type antigen B, and the type AB, who has the antigen on the red blood cell membrane, has antigen A and antigen B. You got to have both to be a type AB person, or who has type O, don't have any antigen. So that's that. So that is 80% of the story. We still have one little thing to talk about, and that is it. All right. So in addition to the cell, here we are talking about the cell. In the plasma, we have something called antibody. Let me use another color. Antibody here. Antibody. So in antibody, so here is the cell. Let me use the red color again. Red cell, especially is red blood cell. That's a red blood cell. We can have a different kind of antigens on the cell membrane. But in the plasma, let's use blue as fluid plasma. Okay, in the plasma, you have something called antibody, all right? In the antibody are produced from the B cells, and this is part of our immune system. So they recognize the foreigners. And for type O person, he or she doesn't have the antigen. They have the antibody anti-A and antibody anti-B. So it has this antibody to X on A and X on B. So this is his or her blood. That he doesn't have any antigen, but he has anti-A antibody, anti-B antibody. For type AB person, it doesn't have any no anti-A nor anti-B antibody. So that's that. For type A person, it has antigen A, and in the plasma, in the blood, it has the anti-B antibody. So when you put this blood into this person's circulation, this anti-B will act on it and it will kill it. So you will have a reaction, you will have a cell hemolysis, inflammation, pain, etc. So you don't want to put type B person's blood into type A person because this B antigen will see anti-B antibody and they're gonna react. For the type B person, it will has anti-A antibody. So that's that. So that's a whole story. So in the cell side, cell membrane, type O doesn't have any antigen, but type O has the anti-A, anti-B antibody. These are two different antibodies, though. So it's not like combined. They are two different antibodies. Each one will act on antibody are specific. So anti-A antibody will act on antigen A. Anti-B antibody will act on antigen B. And type AB doesn't have antibody. Type A has antigen A with antibody B. Type B person has antigen B and the type A and the antibody, anti-A antibody. So that's that, all right? So that's everything. And let's see. So what do we have here? Clear. Oh, here we go. I learned this trick. Thank you so much. All right, so that's that. All right. So let's look at what do we have here. So here is human blood type. This is just the most common way to type a person. They are more detailed or more like a subtype, but in general, we have 4 types: type A, type B, type AB, type O. This one just summarizes what we talked about. Type A person has antigen A on the surface of the red blood cells. Type A has antibody, anti-B antibody. Type B person has antigen B and the anti-A antibody. Type AB has antigens A and antigens B. It doesn't have any antibody against A or B. Type O person has no antigen A nor antigen B, but this person has anti-A antibody and anti-B antibody. So that's that. So this one is just a graph to show you that the type A person has this antigen A, type A person antigen A, and in the plasma it has anti-B antibody. Type B person has antigen B, and he has anti-A antibody. Type AB person has both antigen A and antigen B, but it doesn't have anti-A or anti-B antibody. Type O person doesn't have antigen A nor antigen B. This person would have anti-A and anti-B antibody. So that's that. These are 2 different antibodies. So that's that. Now, another important thing is blood donation is because when a person loses a lot of blood, we need to provide them red blood cell because without the blood cannot transport the body cannot transport the oxygen, so a lot of organ will be injured. in order to save the person, we will provide the person with the red blood cell, but we don't want to create reaction. So for the A person, since it has anti-B antibody, the red blood cell you provide should not have antigen B on it. You can provide with this thing, this red blood cell, it doesn't respond to it. But if you provide with anti-B, if you provide with type B blood to a type A person, this antigen B will react with anti-B antibody, and then you will have reaction. You're gonna cause more damage to a patient. You can provide with type O blood, because type O blood, look, it's so smooth. It doesn't have anything on it. So it will not react with the anti-B antibody in the type A person. So that's that. So that's the idea. Another thing about the blood type is sometimes we have A plus, A minus, B plus, B minus. What's that plus mean? This plus refer to another antigen. So with this one, we will have the antigen D. So let me draw it here. So with this one, sorry, it's working. All right. So this one, we will have a, let me use the right one, easier that way. Here, clear all. Yeah. So use the red one here. Okay. So here is a cell. So it whether that has a B or A or A, B or nothing. So you have these four types. In addition to this, we also know, later we know that there is another antigen associated with the blood typing, which is antigen D. So I can draw here. So here is a new one. So it's the D. So for the type B person, you may have type B without antigen, or you may have type B. So here is B with an antigen. Let me use another color. So this is a D. How can I draw D? How about that? How about that? D, right? So it has D antigen. For type A person, so we call this B plus. We call this B minus. For type A person, this person may have no antigen D, or this person has an antigen D. So that's that. This is A, and here is right a D. So we call this A plus. This we call this A minus. All right. So for example, here we have a type AB person doesn't have antigen D, but he or she may have. Let me use try to be lazy, but I shouldn't. Man. All right. So let me do this one here. All right. Yes. So that's that. So here is his blood. Yes, antigen A and antigen B. No antigen D, but if he has, then we call it AB plus. So here it will be the AB plus. This will be the AB minus. O is the same thing. No antigen A and B, but this person may have D. So if he or she has a D, we call it O plus. So let me show here. So here is D. So this one will be the O minus. This one will be the O plus. So that's that. So with the antigen D, you can either has a you will mark these type as as a plus on top of that blood type. So whether that's B minus or B plus, A minus or A plus, AB minus or AB plus, O minus or O plus. The thing about the antigen D is that there is no antibody D. So for either one, for this blood, so for this blood, right? So that's that. Yes. So that's that. There is no antibody D. So if you put this blood into this person, what happened? If you put this blood, B plus into B minus, if you put B minus to B plus, nothing will happen because there's no anti-D antibody, so it won't react to it. But if you put the B plus to a B minus person, if you do that, let's do it this way. So if you do that, if you put the B plus, so here is B plus blood, here is the B plus blood. So you have a B here, right? So this is B. So they are friends. They are not going to fight, but this friend carry something different. It has a D on it. So here's D. So this is a B plus. If you put a B plus into a B minus blood, because there is no antibody, anti-D antibody, so there's no reaction. However, over time, your immune system will see this, antigen D. And by looking at it, just by timing, it will recognize that this is not us. And the body will create anti-D antibody to recognize it. And then we call this anti-D antibody a sensitized to anti-RH. This is called RH factor, anti-RH or anti-D antibody. Yeah, so that's that. So you may sense it. This could happen when the pregnant woman, say this is a minus, it doesn't, the woman doesn't have the antigen D in their blood, but if the baby has a D on it, the mother may recognize it and then may over time create the anti-D antibody. And then in that situation, the body will build up the antibody, anti-RH antibody. And then by the next time, if she is pregnant, she will have the capability to recognize this blood and to react to it. So that is the situation. Yeah. All right. So that's the RH factor. So here is a picture. So here is the RH factor. You either have no antigen D or antigen, or you have the antigen D. So if you have the antigen D, you will add a plus to it. If you don't have the antigen D, you put minus on it, right? So you have B plus, B minus, A plus, A minus, etc. And in the plasma, the person should not have the antibody D unless it experience the antigen D in the system, and then it gradually build up that immunity and produce the antibody to against that antigen D. So that's that. And that is a situation that pregnant women need to take care, be careful about it. And they are a common procedure to reduce the sensitivity to antigen D. So it's not like very fatal or anything like that. We have the procedure to reduce that sensitivity. And just something that you need to be cautious about. Yeah. So we talk about the donation. We talk about that you need to be careful that the receiver's antibody may against the donor's antigen, and so you need to do let me clear everything, clear our drawing. So the receiver's antibody may against the donor's antigen, and so you need to make sure that you don't have that reaction. So that's called the compatibility test. And basically, you want to know the test basically is to test your blood type. If you're type A, B, AB, O, let me take a look here. So here is your blood type right here. Your type A, B, AB, O. So O blood doesn't have any antigen. So you put this one into this person, to this person, to this person, to even this blood. Look at that, so smooth. There's nothing against it. So O type O is a universal donor. It donates its blood. Everybody can take it. Okay, so that is that. For the universal receiver will be he, this person, because it doesn't have any antigen. So no matter what kind of blood you give it to this person, there's no reaction. So this one, the type AB, will be the universal receiver. It can receive different kind of blood. If the person is a plus, it will have no antibody against that antigen D, so that can receive the blood donation. But if the person is negative, then it may, so you see that. If the person is negative with the antigen D, it may produce the antibody to against the type D. So that will be that will cause a reaction. Yeah, that's that. So let's see. So here is compatibility. Type AB has antigen A and B, doesn't have antigen antibody. It can receive AB. Type AB is universal receiver. It can receive all type. Type A can receive type A only. Type B can receive type A and O. Type B can receive B and O. And O is a universal donor because the O, look at that, so smooth. Nothing will against it. So it can donate their blood to type A, B, and type O person. So that's that. This one just gave you another graph to show you the compatibility test. All right, if there is reaction, if the antibody recognizes the antigen, then it will group them together. This is process of basic immune process. Antibody recognize the antigen. This antigen could be the different type of the blood cells, or could be the pathogens. They will try to trap them, and when trap them, you will see if you do the test, you will see them gathering together. We call this agglutination. Agglutination is processed by the antibody trapped the object that has the antigen match with that antibody. And so you can see the blood agglutination. And this one will kill the cells. So we will have this hemolysis. Hemo means the blood, lysis means degradation. So we have the hemolysis. So that's that. So that's that for this lecture. Let's take a break. And we have the final portion that is hemostasis. And then we will finish it.